The Channel Tunnel stands as one of the most remarkable engineering feats in human history.
Connecting the UK and France, this massive underground tunnel was completed in 1989.
However, this simple train tunnel method faced a significant technical challenge.
Can you spot the issue? Let us look at an example to understand.
When you push the train, the compressed spring resists the movement.
The solution is simple. Remove a portion of the spring to reduce resistance. Similarly, a high-speed train in a tunnel compresses air, creating high resistance. To solve this, 194 piston relief ducts were built to remove the compressed air. Digging beneath the seabed to connect two countries seems like a simple project.
But the reality is much more complex when you look at the soil cross-section.
What if the tunnel collapses due to immense water pressure?
After a detailed geological study, engineers decided to drill through the chalk marl layer.
These detailed diagrams of soil layers were not available until the mid-1950s.
Engineers drilled hundreds of boreholes and conducted extensive geophysical surveys.
These surveys were conducted over decades to understand the seabed's nature.
Even Napoleon Bonaparte had a plan to build a tunnel across the channel. The idea was presented in 1802 during a brief period of peace.
It was a tunnel for horse-drawn carriages lit by oil lamps.
Now, let us introduce the tunnel boring machine, a robotic caterpillar.
The cutter head has many robust cutting tools and portholes. Hydraulic pistons press the cutter head against the ground with high pressure.
As the cutter head spins, the excavated material fills the mixing chamber.
These surveys were conducted over decades to understand the seabed's nature.
Once a stroke is completed, the machine assembles precast concrete rings.
The machine's motion is similar to a caterpillar's, hence the name.
These giant machines were transported piece by piece and assembled on site. They were manufactured by the Robbins Company and Kawasaki Heavy Industries. Assembly occurred at construction sites near Dover and Sangatte.
Massive underground caverns served as assembly halls for these machines. A skilled team worked for weeks to assemble one tunnel boring machine.
The project required 3 tunnels, 2 main ones and a service tunnel. Cross passages allow access between the service and main tunnels.
Maintenance personnel use the service tunnel to access the main tunnels.
Engineers had to follow a strict tunnel axis under the seabed.
Once a stroke is completed, the machine assembles precast concrete rings.
Surveyors initially used traditional triangulation techniques.
High-precision electromagnetic distance measurement instruments were also employed.
GPS technology further helped with surface surveying.
Shaft plumbing accurately transferred surface survey coordinates down to the seabed.
A zenith plummet was set up to measure accurately.
Combining all data, engineers established the tunnel axis.
The computer in the control cabin informed the driver of any errors.
Periodic adjustments were made to ensure the path remained correct. Grouting was injected to strengthen the soil before drilling.
Probe holes were drilled ahead to check for unfavorable conditions.
Radial drills helped in grouting for the main tunnels. Soft docking was used to safely meet the two tunnels. A 5-centimeter probe was used to confirm the alignment.
The historic handshake moment finally arrived on December 1, 1990.
Finally, the French TBM broke through the remaining ground.
The machine breakthrough was a moment of celebration.
The tunnel design included 2 crossovers for maintenance.
These crossovers divide the tunnel into 6 manageable sections.
This allows maintenance work while keeping the tunnel operational. Surveyors initially used traditional triangulation techniques.
Axial fans were installed for fresh air supply.
Fresh air is supplied to the service tunnel at both ends.
It flows into the main tunnels through controlled louvers. Cross passages connect the service tunnel to the main tunnels.
A total of 11 TBMs were used for this project. Different geological conditions required different TBMs. Some machines were intentionally buried, a TBM burial procedure. Dismantling and transporting these machines was a costly affair. Pipes carry chilled water to absorb the heat.
This maintains a safe temperature of 25 degrees Celsius.
The train enters the Channel Tunnel on the French side.
The train follows a complex path through the chalk marl layer.
This massive underground cavern is an engineering marvel.
Crossovers allow traffic to be rerouted during incidents. Maintenance vehicles enter through the service tunnel.
Personnel enter the running tunnel to perform maintenance.
Pipes carry chilled water to absorb the heat.
The train exits the Channel Tunnel on the English side. The train turns around for its return journey.
We worked on the channel tunnel project for over 4 months.
If you are impressed with this content, please subscribe.
Please support my channel and educational activities.
Take care. Bye-bye. Niga, bye.
The train turns around for its return journey. If you are impressed with this content, please subscribe.